Hi, I'm James from Practical Neuron, and I will show you how we got our neural network configured for image classification. So here we have all the Python imports. We load the data. We define that we have 10 classes. We define the shape that the data will be in. We scale each value. They're up to 255. We want them between 0 and 1. So we divide by 255 and expand the dimensions. So that way the neural network can actually read it. And we look at 60 training samples and we test on 10,000 samples. So here's what the samples look like. They're handwritten digits, they're images, 28 by 28 pixels. Here we create the baseline model. This will actually use 32-bit floating point, full precision floating point values. And then this is the neural network that will use the quantized weights. It's the exact same size. All we do is we loop through each weight and quantize it. So here we train the baseline. This is a small look at quantization. Well, here is the accuracy of training the baseline. We get up to about 94% accuracy in this case. And then as soon as we go, if we change the bit width down to 1 bit, we only have about a 12% accuracy. But if we go up to 4 bits, we have about a 93. And then anything higher than 8 bits will have about a 94% accuracy. So we used an 8-bit for our FPGA implementation. So thank you.
Quantization is the process of taking a continuous input and turning it into a discrete input. In this project, we use quantization to take an n-by-n system based on 8-bit quantization. Quantization has to be carefully implemented to ensure minimum loss of accuracy. The 28 by 28 pixel grayscale input image is quantized from its original range from 0 to 255 to a range from 0 to 121.
Hi, I'm going to talk to you about our hardware implementation on an FPGA board, the hardware portion of the inference engine. First, I'll talk about our results before delving into the hardware path. Our results were very good for implementation on FPGA. We had a relatively slow clock, only 50 megahertz, but we're still able to achieve an execution time of about 250 microseconds per image and giving in greater than 90% accuracy over 1,000 images, which is very good compared to a general purpose CPU in terms of execution time. So for our data path flow, what would happen is we would have 4 basic memory modules. The first is an image RAM, where the quantized values of our image, our base image, are imported. Then we'll have a weights ROM, where quantized weights are just stored in a ROM. Same with bias, quantized bias is stored in a ROM. And then our final memory thing is called a sigmoid ROM, which contains sigmoid values. Sigmoid values are just squishing a value between 0 and 1 using a math function. And the values for that math function are stored in a sigmoid ROM so that we don't have to do the math in hardware. So how it would work is an address from the image RAM and the weights ROM are read, multiplied, and then added to an accumulator for all of the first layer, and then eventually a bias will also be added to that. And then that value will go to the sigmoid to get squished between a 0 and 1, and then finally stored into a register file, and eventually back into the image RAM, because the middle activation outputs will be used as the image RAM for the next layer. And that same path will happen again, and you'll get 10 output things into the image RAM, and the highest of those 10 values will be what the system predicts. Thank you.
There are several neural network applications for our senior design project. Our all neural network can take a given image and recognize the handwritten digits 0 through 9. Another image recognition application could have a neural network determine if a tank is present in a given image. This could be useful because it can sort through numerous amounts of pictures and videos and can identify if a tank is present. There are other applications that you could use a neural network for, such as signature verification and speech recognition.